Good morning again. Let's see the next lecture now. Welcome to our next session. Now, in the first session, we discussed about the MIPS processor, right? So it's as I said, it's an evolution of parallel processing. Now we have the multiprocessor system. Means it's an advanced version of that MIPS. Now, when I say multi, so nowadays we use number of terms related with multi. I mean, like we have multi computers, multiprocessor, multitasking, or you can say multi-core systems. So multi-programming. Then we have means lot of means sometimes we feel a bit confused. Means how these terms different from each other. Well, as the name said, multiprocessor means we have more than one CPU in a system. So obviously, if I arranged in you can say descending order in terms of the integration. So microcomputer, multi-computer is at the top. Means it consists of a number of computer systems, right? Each has its own processors and all, and they are put it on one chip. Right? That's called a multi-computer. Then we have multiprocessor. Means in one system now we are talking about the one system. Okay, in the one system we have multiple CPUs now. Okay, so then we have multi-core, which is you can say quite a familiar term. Even everybody knows more what I mean by multi-core, 2 core, 4 core, like that. So what happens in that? So in the multi-core systems, so every task, like you have some task to do with the processor. So that task is divided into different units. Means access part is different, programming part is different, control part is different. So every core or every part is assigned to some different unit specifically performing that particular task. So that is a multi-core. Similarly, we have multi-programming, multi-threading. So all those networking concepts. Okay. So the multi-core, they are further means every constituent or every part is done through some different unit. So means at the top we have multi-computer, then you can say multiprocessor, then we have multi-core, then you can say multi-threading, even multi-threading, multi-core. Multi-threading is further multi-programming is further multi-threading, means a further subject, task of further subject. All those things, all those terms, they are used for the parallel case. Means they are, we want for the faster communication, or the things to be faster. We don't want that we should wait for long to execute any particular set of instructions for too long. So we want to decrease its execution time. So what we've done so far, that their task is divided into number of parallel streams, right? So every stream is given a one particular task, so they do it separately, and then they are combined to a sync. There's a major problem that we're going to see in the later on slides. So these are about the introduction to multiprocessor systems. So basically these are three different architectures, prime architectures that shown. So one is your there are three types. They're just introductory part, right? Later on we discuss them in detail. So first we have shared memory models. So the part A, you can observe that we have some common memory space. So C stands for CPU over here. So we have shared memory space. So that memory is shared between all the CPU, between all the processors, right? Then we have second, your message passing multiprocessor. So in this case, we have different CPUs. So they have own physical memory associated with it. And all those CPUs, they are connected with each other, right? Through this interconnected network. Now they are on how they are connected, that we want to say there are switches out there actually. So it can be 2 into 2 switches. It can be your different stages of switches. It can be one stage, two stage, three stages. It can be any number of stages. Means they are connected through such stages, right? So means if like in the shared memory, so we have a common memory. Means whatever we want to read or write from memory, we have to specify particularly. Otherwise, during the sharing, the sync is the major bottleneck, you can say. Okay, then the second B part is a message passing multiplexer, right? So means if any CPU out of this configuration, if want to communicate with any other CPU, you have to pass the message, right? Means that's why it's called the message passing. Otherwise, if we want to execute its own, then they have its own memory, own processing unit. So if you want to, if he needs to communicate to pass its result to the any other processor, then he has to go over the message passing multiplexer. Then wide area distributor part C. So here you can say it's widely distributed over a wide area network. Means this is a particular network concept is there. We have a complete system. Every individual entity, if you see the part C, so every individual entity, it can serve as a complete system. Okay, so all those systems are connected through some networking or some internet, right? That's why it's wide area distributed systems. There are three basic types. Then we can say how they are different. There are three main things: main multiprocessor, then multi-computer, then distributed systems. You see in terms of NOR configuration, Microsoft, obviously we have CPU, multi-computer we have CPU, RAM, and some interface. Then a complete computerized system in your distributed system. Then we have a node of peripherals. So all are shared, because then if you follow the sharing configuration, then we have shared execution and in maybe disk. Then location means the same rack. Everything is in the same rack. Then we like multi-computer, you can say in the same room. Okay. Then possibly worldwide in a distributed system. Then intermode communication using a shared RAM. Then we have dedicated interconnect. Then we have traditional network, right? Then operating system, that can be, we'll come to that later on, that there are different OS configurations also there. Means how they are connected basically. So they're shared one in the multiprocessor. Then we have multiple in the like computers. Means every system has its own OS, right? Then possibly all are different in the distributed system, right? So if you talk about the file system, it can be shared. It can be shared similar in the multi-computer. But yeah, in distributed, each node has its own file system. Then in the administration, we have one organization, and more organization, right? So these are just a basic comparisons that how these terms they are different from each other, right? So as I discussed, if we start from top, we have distributor system, then we have multi-computer, then it's part means at the top distributed system, then the multi-computer is its part, then we have multiprocessor, then we have multi-core, then you can say we have multi-programming, then you have multi-threading. So all those multi things means they just lead to your parallel processing, so that the processing can be faster. Fine. So now why we choose multiprocessors? So as you said, we have more than one CPU in the multiprocessor to improve our performance. And basically even it can say that one CPU meant for one user, another user means every user can do the independent task. Okay, that's why you can say it will support your multiple users also. Well, we have multiple applications, obviously, so each CPU can do its own applications, right? multitasking within an application. As I already told you, the order, okay, in which hierarchy, otherwise correctly is your hierarchy speaking, means if you see that hierarchy, so multitasking is obviously it is there, means then we have multitasking. Further, you can call it as multi-threading also in the networking point of view. All right. Then we have responsiveness. Otherwise, it will increase the throughput also, right? Then, but we have to share the hardware between the different CPUs. Symmetry is the most major issue in a multiprocessor system. When we have more than one CPU or more than one processor, then the obvious task is to maintain the coherence or the sync between all those processors. We come to those protocols that used for this purpose. Okay, so in a multiprocessor system, all CPU may be equal, right? Or some may be reserved for special purpose. Yeah, as we seen in the MEMS processor, we have some co-processors, right? So similarly, we have more than one CPU. So we can, if you want, depending on the need of your application, you can reserve one of them for a particular application for the special purpose. Okay, so a combination of hardware and operating system, yeah. Then software design constellation determines symmetry, means like we have more than one CPU. So how they can perform means you have to decide the order. Like it means they should operate in which order, or they should operate parallelly. Means you will divide your task, multiple tasks, and they will combine. So that combined order they will decided by the software you design. So system that treat all CPU equally, it's named as metric multiprocessing. Okay. So similarly, if all are equal, we call as metric. If it is that they're not equal, then the system sources, there are a number of ways which we can divide those. So it is called as asymmetric multiprocessing. And similarly, non-uniform multiple access, we'll see later on what these terms mean. Then we have clustered multiprocessing, right? These are all the examples of all asymmetric multiprocessing. So, well, if you see from the instruction and data stream point of view, we can use this multiprocessor in a different ways. So one is called a uniprocessors, right? Actually, a single processor itself, you can call it as a uniprocessor, right? So uniprocessor is your single instruction, single data system. It's called SISD, single instruction, single data. So in the slide, we are discussing that how we can use those different data streams. Means then single instruction, single data. Then similarly, within a single system, you can execute multiple independent sequence of instructions, right? Then in the multiple context, obviously. So then such types we call as MIMD, that is multiple instruction, multiple data. Means in a single system, you are executing some multiple instructions and which deals with multiple different data streams or data types. We call MIMD, which is you can say the most advanced version of your parallel processing. It's MEMD, means obviously the system got complex in this such cases. The third type is that a single sequence of instructions in multiple contexts. Usually that is your single instruction, multiple. Usually this thing normally we not prefer because it's simply just for the case that resource utilization is not that good in such configuration, that is single instruction multiple data. So that's why out of this then we are last we have multiple sequences of instructions in a single context, that is your multiple instructions and single data. So you can say there are four types: SESD, MIMD, SAMD, and MISD. So out of those, usually we prefer MIMD because the resource utilization will be good or better among all the other combinations. Now, as we discussed so far, we said that we discussed that it contains your multiprocessor, it contains the more than one CPU, right? So how they are connected means those processors, or you can say those CPUs, how they are connected. So it can be connected in two types. One is called tightly coupled multiprocessor system and loosely coupled multiprocessor system. Yeah, so in the tightly coupled, it contains a multiple CPU that are connected at the bus level. Bus level, you will topologies you know already. Okay, so we have single bus. Okay, so every CPU, multiple CPU, whatever be the number of CPUs are there in your system. So they are connected on that single bus. They are they're widely connected to that bus, and these CPU may have access to a central shared memory, as we done in the last slide. We have SMP and ASMP, symmetric multiprocessing and asymmetric. So this can be called it as symmetric because that bus or that memory, you can have the shared memory, so that are shared equally among all the CPU. That's why it's called a symmetric multiprocessing. Or it may participate in a memory hierarchy with both local and shared memory. Okay, so you can say non-uniform multiple access. So in this NUMA configuration, each CPU has there are two types of memories, means local and shared. So each CPU has on private local memory, but yeah, some shared memory is also there. So these are some examples, right? There's where IBM P690 Regatta system is there. Then we have chip multiprocessors. Okay, so it's again, as I said, that it's a era of parallel processing. Means we have multiprocessor, then we have multi-computers, and now it's an era of interdisciplinary kind of things. So nowadays we are using this MPSOC, if you heard about that, a multiprocessor system on a chip. Nowadays means all those processors, it comes a system on a chip, means they are single chip or their whole system is on a chip. Nowadays we are going for that. If you heard about let's say you may heard about the Sony PlayStation 3. So it's the latest example of this MPSOC configuration. It's a multiprocessor system on chip. Okay, fine. So they are connected tightly coupled, right? So then we have loosely coupled multiprocessor system. So it often it is very often we refer to as the clusters, right? So based on multiple standalone, single or dual processors, they are completely computers. They are interconnected via high-speed communication systems such as Ethernet. We have Linux and web full cluster is there. Okay, so means we have different system and they are connected to some intermaking, some communication system called as loosely coupled. All right, so in the very first slide we discuss this architecture. So now we see in detail the multiprocessor communication architectures. So in the message passing, first time we do message passing. So we have in such cases we have separate address space for each processor, right? So processors communicate by message passing. So means if I want to share my result, or if let's say if I am executing any process and that process needs some result from the other CPU, so then I have to communicate with the other nearby processors in the same system, in the same processing system. Now I have to communicate by the message passing. We have to pass the message, then it will acknowledge, then we'll read and write all those things. Then yeah, processors have their private memories. Means if in a single system, if a process does not need to use the resources of the any other processors which are lying nearby, then they have their own memories and they can execute their own process. They need not to pass any message to each other. Then it focuses attention on costly non-local operations, right? So in the shared memory, we have processor communicate with shared address space. Means all memory is shared among all the CPU, right? The processors communicate by memory read write. Yeah, means then again we discuss one problem later on in the later slides. Like we have multiple processors, if all of them try to read or try to write at the same time, Then how will they manage? So we have Snoopy protocol for that. Snoopy and MESI that we discuss in the later slides. Yeah, so it's easy on small scale machines, lower latency. Yeah, then SMP or NUMA and UME is examples. So there, if you particularly target the shared memory processors which are used quite a lot, so we can divide the access. Its access is in two different types. One is called a uniform memory access, that's UMA, and you can say non-uniform memory access, that is NUMA. So what happens in UMA machine? I'm showing here the it's UMA uniform memory access block diagram. So what happens in that? A single copy of OS operating system, a single copy of that. Okay, although some parts may be in parallel, but it depends on the need of your application. Okay, so they are single copy of OS. If you see in the diagram, we have each processor has its own cache memory, and means there are two types of memory, local and cache memory, and some other physical memories there. So they all connected through some interconnection network. Means it can be a switches, it can be it can be some topology, it can be anything. So that's why I use a generalized term. It can be interconnection network. Okay, so it contains the single copy of OS, relatively easy, obviously, because in this we have same OS. Accordingly, we can program the different processes. Okay, but yeah, it has one problem, means you can't. There is a limit to it. You can't scale up to a larger number of processors. Means at that time, means if you go on increasing the number of processors, then it's to maintain a uniformity access, uniform multiple access is a bit difficult over there. So scalability problem is there in your world. So as it goes, there are two types: uniform memory access and non-uniform memory access. So in the UMA, we have access to all memory at the same speed for all processors. So that's sometimes you can say it's difficult to achieve. Also means what we ideally what we want, that whole memory should be uniformly accessible to all the processor and with all same speed. That's why there is a scalability problem. Means if I go on increasing the number of processors, then it may happen that the speed will change. Means some processor will have access at higher speed, others may not have. Okay, so there's a problem that. Then non-uniform access, they are sometimes also called distributed share memory. So typically, interconnection, it can be a grid, it can be a switch, it can be hyperconnection, any type of interconnection we can follow. So access to some parts of memory is faster for some processes and other parts of the memory than other parts of the memory. Yeah, so that's why it's called the non-uniform. Means some parts or some processors may access faster to that particular memory, some may not. Okay, so means we have to put the hierarchy. Means that we have to decide in the kernel and all. We have to decide that which are more important. Or sometimes some processors need a frequent access of the memory. So it means that will they're the top priorities. So means it's non-uniform. Obviously, they're meant for. Yeah, it's harder to program. Okay, but yes, we can scale it to more number of processors as compared to your UMA. Means we can scale up with a large number of processors. Means obviously there is a problem with UMA that there is one characteristics that each processor has the same speed, so which is not required, which is you can say it's not possible in practical cases. So that's why you are in NUMA. If you go on increasing the processors, obviously the access speed will vary. Okay, so now we see the basic architecture of the UMA. One of the simplest one is your bus based uniform multiple access. So it's the simplest microprocessor, multiprocessor. So we have more than one processor on a single bus, and it's connected to a memory. So, but again, if you go, there's one problem is speed that we discussed, the memory speed, or you can say access speed. Other problem is the bandwidth. So if you go on increasing the number of processors, then the bus bandwidth becomes a bottleneck. Means you can't You can't increase beyond some limit, right? So each processor has some cache to reduce the need to access to the memory. Now, as I said, now in the UMA, so memory is accessible to all. So if let's say we have number of processor and every processor tries to access that memory, then memory sync problem will be there. So to avoid that, what is done in UMA, that each process provides some cache memory in it. So sometimes if we need to store some temporary results, means then those results are stored in the cache memory, and that can be used. Means in such cases, when you are using the cache memory, no need to access the primary memory or the logical memory. So means uh, the memory, it all depends on how you are handling your memory space. To further scale the number of processor is, yeah, that's what I talked about. To further scale the number of processors, each processor is given some private local memory. Means still there is a possibility to scale up the UMA by providing cache memory or to the private local memory to each processor. Means sometimes, as I said, to store some temporary results, you need to, for those temporary results, so it's need not to every time go for the private local, every time for to the access on the memory, main memory. So that purpose can be solved by using the cache memory or some private local memory. So there are different types of hardware possibilities in case of UMA. So first is first possibility is that how can you connect the different processor. You can see in the A type. So all their CPU, they are on the same bus, and even the memory is on the same bus. Means all the CPU, they are sharing this memory. In the B type, we have some shared memory along with some cache memory. So in the B type means every CPU have some cache memory with it. So then we have shared memory. So means both possibilities. We have cache memory as well as some shared memory or the shared memory. So they are on the same bus. In the C type, so every CPU is provided with its own local private memory along with cache. So means why it is done, so that it will least access to the shared memory. Otherwise, if every time it will access to the shared memory, then obviously the process will be slow, because we have multiprocessors in a queue. So we have to access, means memory can be accessed accordingly. So if they have their own cache and private memory, so their chances of accessing the shared memory will get reduced. So due to this thing, we can scale up to a larger level. That's why we can increase it to some extent, right? Yeah, it's a second type of connection that you can do on the left side. We have different CPU, then we have a different set of memories, row and column wise. Okay, so every depends, it can be any number of CPU, any number of memories. So every CPU and every memory assign some code. You can vary accordingly. Okay, so they are interconnection bar, you can say here. So any CPU can access to any memory, so they are connected through some switch or network. Okay, so it's a crosswalk kind of switch. Okay, so here is shown that if a switch can be closed or switch can be opened. So if it is open, it means that CPU is not connected to that particular memory. So if a particular CPU want to connect a particular memory, so that particular link is closed, or that a particular switch is closed. Okay, so by this you can scale up to n number of your CPUs and memories. In the third type, now what about the switch? Switch can be scaled up. Scale up, it can be a 2x2 switch, or so UMA multiplexers. It can be a multi-stage switch. It can be means the switch. It can be multi-stage, single stage, or it can be anything. 2x2, 2x4 means multiples of 2. It can be anything. So this is the third type, in which we have 2x2 switch. Okay, so its message format will be some again some module address of code and some value if you want. Yeah, fourth type, sorry. So it will call it as a mega switching network. You can say on the extreme left we have CPUs, list of CPUs, then extreme right we have set of memories. So then in between we have different stages. Here I shown the 3 stages of the switching, right? So means I marked with some A and B path. You can see how this A path grows. So in the stages I marked with the switches stages I marked with the ABCD. That's 1A, 1B, 1C, 1D, the first stage. Second ABCD is second stage. Then we have third ABCD, the third stage. So switching, there are different stages. So you can see the path A and B. So that goes to the different stages. So CPU can connect to a particular memory through this different stages. So for type of hardware. Actually, it is no. It's just the way of just assign a particular code to that. It's not actually there. It is just means like we have some logic codes and all. Means we just distinguish the one CPU from another. Means these data are 00 or 001 there. It's not actually written over there. Okay. Hmm.
Used to access the memory location that 010.
Hmm.
Third,
Hmm.
first box needs
anything.
alternate access. There is no class.
Well, this is accordingly you can. This is the one example that I shown. Right? It's not a fixed one. You can program it accordingly. It's a, means you have it's hardware as well as software. That's why according to the switch mechanism will be changed. So otherwise, if you follow the same mechanism, obviously it will go to a different number of stages. Means that a switch is so programmed. Means it is a programmable thing. It's not a fixed one that this switching is always. It should be like that. It can be changed accordingly. Just one example that I shown means accordingly you can program these switches. It's not the fixed one. Okay, you can program it accordingly. Then we have till now we discussed the uniform multiple access. Now we have NUMA, non-uniform multiple access. So all the memories can be addressed by all the processors. That this is you can say nothing is private. You can say means the shared memory is there. So all the memories can be addressed by all the processors, but access to a processor's own local memory is faster than access to other processes remote memory. Yeah, obviously. So it means the access speed will vary. This is the major bottleneck in UMA. UMA we want that the access speed should be remain same, but it does not remain same in NUMA. Means the speed to its own memory obviously it will be faster than speed for the accessing the memory of other processor. Okay, but it can access those. Okay, so it look like a distributed machine. Yeah, but the interconnection network is usually custom designed switches. Or that probably answer your question. It's a custom designed switches are there. Okay, so or buses. So you can say every processor its memory and I/O devices. So means peripherals. So similarly with all the processors and all those processor, every processor is associated with certain on memory and I/O devices. So they are connected through some interconnection network, right? So obviously if processor 1 want to access the memory of some other processor, then obviously the access speed will be slow. So it will he can access through this interconnection network, then but the speed will be slow as compared to its own accessing the own memory. Now, how this operating system behaves to such configurations? So the 3 options. Option 1. So in case of a CPU, statistically allocate the physical memory to each CPU. So that's what we are discussing so far. It's OS option 1, that each CPU run its own independent OS. Okay, but peripherals are shared peripherals, and each CPU handles its processor system calls. But it's used earlier multiprocessor means every. Actually, again, there is a problem. If every CPU runs its own OS, then again, to communicate, if one CPU want to share some data with CPU 2, 3, and all others, so sometimes the compatibility issues will be there. Obviously, there we have to program it accordingly. So sometimes it's difficult. Okay, so it avoid concurrency issues while not sharing. Okay, so issues are, what are the issues? Each processor its own scheduling queue. Obviously, each processor its own memory partition. Consistency is the main issue here. Means because every CPU will itself behave as a independent unit. So when you combine it or when you share it on a single bus, sometimes the sharing is consistency is required or concurrency is required between all those processors. And option two, yeah, master slab multiprocessor means so one of the CPU will act as master, other one to follow that. That's what the master slave configuration, right? If you see in the figure, we have some bus. They are shared by all the processors. Okay, we have master slave operating system, then Streamlit. We have master turns OS. Then we have slave, then along with the other processors. So OS mostly runs on a single fixed CPU. User level applications run on the other CPU, means one OS or the one master, then the one which you marked it as a master, so it has that single fixed CPU. So other processors that are connected to it, it will be you can run your applications on the other CPU, but not on the master CPU. All the system calls are passed through the master CPU for processing. So we need less synchronization in such case, because they're going to follow whatever the instruction the master gives. They're going to follow the other slabs. They're going to follow. Okay, so simple to implement. Yeah, means centralized scheduler is there to keep all processors busy. Means they have to accordingly schedule up. We have to accordingly schedule up the things accordingly. Memory can be allocated for all the needed CPUs. Then, but there is one issue sometimes. Means master CPU becomes a bottleneck. Means how much you scale up. Means so there is limit to it. You can't connect the large number of slaves to a one single master. Okay, so we have master CPU, number of slave CPU, and some user processors and OS with some memory, then some IO devices. Yeah, third option. So it's a bit superior to your master. It's kind of that only, but you can say it's basically based on the kernel based processors. It runs on all the processes where while load and resources are balanced. Okay, so one alternative is that the single mutex is there that makes the entire kernel larger critical section, and only one CPU can be extended in the kernel at a time. Okay, so it's a bit better alternative than the master slab. But the code is mostly similar to uniprocessor code. So hard part is that identifying independent parts they don't interface. So it's a bit the issues there. So it's very difficult to maintain that, solve this issue. So these are some examples, early examples. This we start with. Then we have integrity center. This is one multiprocessor that suggested by the HP. Okay. So it says two 16mm in tandem two processors, and one TV is DDR. Means this is one of the examples of two examples of the multiprocessors. But as I said, nowadays we go for MP source type of communication. So which is, you can say, inbuilt. There are multiprocessors which are inbuilt on a single system, right? So yeah, now seen the architecture so far, the different models, modeling concepts till now that we can model your multiprocessors. Now we will discuss the problems. Means obviously when more than one CPU is there, then the problem will came. First problem is your coherence problem, cache coherence problem. So when it will be, so if shared memory with, if we have no cache memories are there, means we have only shared memory with no cache memories, then let's say processor P1 writes, processor P2 can read, so only one copy of data exists in memory. Means in the shared memory we have only one copy. The P will write, P2 will read that. But if they are if we have if you see that in the message passing I shown in the third distributed type, means every processor have its own private memory and cache memory. So at that time there is a coherence problem, because how it will be. So cache store their own copies of data. Obviously, their three copies can easily get inconsistent. So we discussed in the last slides also, means uh, consistency is a major issue if you have more than one CPU or the processors. So let's say we have just take an example. There are two processors. Processor one loads its some, means they are doing some processing. So it has some value, loads its value, adds its some value, and stores its new value. So similarly, P1 cache now means once it's stored, So in the memory, once the whatever the P1 data it has, it stores it to a memory, then there is no need to keep it the copy of that. So P1 cache will be treated as some dirty data. Similarly, P2 loads also on the memory. It will load that data, means read that data, add it, means then change its value, then again stores that value. So now once it stores, it means no need to put in the cache again. So P2 cache will again has some dirty data. So eventually P1 and P2 cache data is go to the memory. Means you know to put the copy in the cache memory, they go to the memory. Now means we have to keep the right order in view. Means who is writing at the memory, means either P1 is writing or P2 is writing. Let's define it more clearly. What will the exact definition what we are looking for? Let's say A read R from address X on processor P1. Okay. So obviously it will returns some value written by some most recent write W, R for read, W for write. Okay. So it will return a value written by the most recent R, W to X. X is, you can see, some address in the memory on P1. If no other processes are written to X, which means obviously what actually happens. So first it will read some contents from address X using R, then it will update its value, means do some did some processing, then it will write that value again using W to X. So in between R and W, so we assume that there is no other processor written in between them. If P1 write to X and P2 reads, then X after a sufficient time and there is no other writes to X in between. So P2 reads the value written by the P1's write. Means so we have to maintain order. Means initially P1 reads, P1 updates, then he write it again. It's updated to the memory. So in the meantime, the P2 should not write. So it will P2 should read. Okay. So the third part is that if the writes to the same location are serialized, then you can say there is no coherence. Means we should have to serialize that. So there are three properties to define this coherence. So again, as I said, we have to preserve the program order. Right? Means if P1 writes, P2 should read. If P2 should write, P1 should read. It should not means both writes should not be there. Otherwise, the things will be unpredictable. Means whatever the memory has, we can't say. So we have to preserve the program order. And the property 2 says that any write to an address must eventually be seen by all the processors. Let's as we discussed in the multiprocessor system, in the shared memory case, if one processor writes to the memory, then other processor must see it. Means if let's say P1 writes to X and P2 keeps reading it, P2 must eventually see the new value. Means if P1 writes to X, let's say we have P1, P2, P3 and so on. So out of that, if P1 writes something to X, X is the address. If he writes something to X, then it should be visible to all the remaining processors. It should be, that's why it's called the shared one. Means that write result, it should be shared by, that will be read by all the other processors. It should not be hidden. And third is preserve causality. Means suppose X starts at 0, processor P1 increments X, and processor P2 waits until X is 1 and then increments it to 2. So processor P3 must eventually see what when X becomes 2. Means all the processors, they are synced. That's why it's the coherence. Means if I write something, then it should be come to the knowledge of all the other remaining processors. If different processor could see writes in the different order, so P2 can see P1's write and do its own write, while P3 first sees a write by P2, then written by P1. So now we have two processes that will forever disagree about the value of A. Means that's what I want to say, that if multiple writes are there, then you can't say which value actually your memory has. So we have to do the causality accordingly. So the solutions for that, maintaining such coherence, hardware schemes, we have some, there are software and hardware schemes, both are both options are there. So in the hardware scheme, we have some shared cache. So primarily it enforces the coherence. In shared cache means whatever the cache memories they have, we will also make them shared. Okay, but obviously they're not scalable. Means it's up to some limit. There's some bottleneck is there. Now, Snoopy is there. We have some Snoopy protocol that we see in the next slides. So it needs a broadcast network like a bus to enforce coherence. Means uh, if I write something, if P1 writes something to a memory, then it will be seen by all. It should be possible by the bus. Means it should means if P1 is right, then P2, P3, P3, P4, whatever it may be, it should be read for them. Okay, so then that is enforce coherence with a point-to-point network, and a block just one place, the full sharing is kept. So that we already talked about the consistency and replications. We need to replicate improvements. We have to update accordingly. Means if we write something to the memory, then rest will be in update mode. Means all the other processors should update their values accordingly, or they should read and update accordingly. So how to keep consistency? When a processor changes the value, when a processor change the value its copy of a variable, then others are invalidated. Means there are three control signals kind of things, you can say. Variable means they will update the value, or modified, you can say. Then invalidate and updated means once I write something, if I am processor P1, if I write something to X, then other processor, whatever value they stored in the cache, they should invalidate that value, because whatever the current value is updated. So whatever the current value they have other than P1, other processor, they must have their own values. They should invalidate that because the current value is updated now. Okay, so they have to sync accordingly with all other remaining processes. Let's say, for example, if P1 cache has some 1, P2 cache has some 1, then exact that, then the main memory should be 1 again, means it is the exact coherence. But when the problem will come, let's say X is 3, means in the P1 cache the value is updated from 1 to 3, but in the main memory still it is 1. Okay, so it is the wrong way, means there is this is wrong actually. The correct one is if there are three in the P2 cache, then obviously in the main memory should be 3. Means there's a difference between invalidate and update protocols. The first case, if P2 they are storing some data which is the older one or the older copy, they should must be invalidate that. First of all, they should invalidate that copy, and you should write the P1 cache and accordingly update that. So the first case is show the invalidate case, and the second one is your update case. So now the software part. So the how you can manage, or how can you achieve the coherence? So the two protocols they are suggested. So one of them is Snoopy protocol. So by this protocol, you can maintain the coherence between the processors. So how it is done? Each processor, so for every cache object, it keeps a state that can be. So there are three states are designed for every processor. One is invalidate, exclusive, or read only. Okay. So what is our goal? So if one has exclusive copy, then others should have the invalidate. That's what I'm saying regularly. That if I want to write something, so it means I am in the exclusive states. I want to write something. Then the other processors, all the other remaining processors, which is in the same system, they must have their own copy at that time. So they must invalidate that copy because I want to update, I want to write something. So they must invalidate their own copy so that they can read the new one. So there are three types of messages when they are designed in the Snoopy protocol. One is your read request, write request, and the value response. So we'll see what will the meaning of these messages. So we made two assumptions. If there is a contention on bus, then you can say it means if there are two writes, as generally happens. So only one will succeed. It depends on what the priority will assign. And there is no split transactions. Means whenever you put read request on a bus, then it should be followed by VR. There is value response. It should be acknowledged kind of. I mean, it should be responded by some VR, the value response, right? So protocol is called Snoopy because everyone is listening to the bus. Means all the time. Means all the time, all the processors they are connected to its bus and they have to update their data accordingly. and update state in response to your message read and write. So each cache controller responds to the 4 types of events: read or write, or response to these messages: read request, or as you can say write request, or the value response. Now we'll see how this coherence will achieved with this. We will see its details, the protocol details. So as I said, there are three states. So a state can be in read-only mode, it can be in accuracy mode in the Snoopy protocol, or it can be in the invalidate mode. So if it is in the read-only, so it can perform these four operations. So if it performs the read operations, so obviously if it is in the read-only mode and it performs the read operation, means it will obviously return some local value whatever is stored currently. And if you want to write, then he has to change its state to occlusive, obviously, and update whatever the value is stored. So it should write or it should update the local value that it has. Then write message on AWS. So it updates to, means once it's write, means if I update my value, I go through the occlusive, I update the value whatever it has, then I have to invalidate my own copy, because we have to give a chance to the other processors. They may write also. So once my write is complete, then I have to invalidate my own copy, because I must give a chance to other remaining processors to write or to modify that. Okay. So read, if I want to read only message on the bus, then it should broadcast the value. The value response should be there. So RR is always followed by VR. That's read request is always followed by the value response. Now, if the state is already in accuracy mode, so then obviously they're going to write something. So if the read operation means it will return some local value, again as we done in the first case. So if you want to write, if it is in the write operation, then it will obviously update value. Then if you put the read request message on a bus, then again it will be followed by the VR message. It will, the response should be the VR, and it will, so once it's write, so then it can be, means if the write is complete, then the next stage will be read only, means other processor will get a chance to write. Then at that time the occlusive state should change to the read only, because we have other processors may want to write, so we have to give them chance also. So but if my state is already in, I am in the invalid mode, then if I want to do the read operation, then again I will broadcast RR message on the bus. Then it should be responded by the value response. If I want to write, so as in the first case, means if you are in the invalidate mode, you can't write it. You have to switch yourself to the read only mode, then you can write. Okay, so VR messages on a bus, they have to update accordingly. And if you are write, you can write on a bus and do it accordingly. Means there are three stages we generally design in the Snoopy protocol. So sample scenario, assume we have three processors, P1, P2, P3. We were just considering one example. So let's say initially P1 is entry, P1's entry for the X is invalid, means P1 is in the invalid state, P2 is in the exclusive state with some value 3. Means exclusive state means I want to write something. Let's say I want to write 3. So that's why P2 is exclusive with value 3 and P3 is invalid mode. Again, means the one case. So I just consider one example, right? So a process running on P3 issues, obviously it will read, then P3 send the message, because P3 is invalid state. Okay, so in the last slide I discussed, if it is an invalid, then it must go for the read case. So it will issue the read, then send the message. Then once it's read, it will be response by the RR message. Okay, read request, then it must be followed by the value response. So value is already written by the P2, that is 3. So the value is he will receive the VR message with X is 3 on the bus. Okay. So P3 updates his entry to read only now, because P3 is initially invalid. Initially is in an invalid state. He will issue the read write request, read request message. He will be responded by the VR message. Then he will go to the read only, because now instead of invalidate, now he got its own current copy, whatever we know on the X. Okay. So he will be now in the read only. So to record the value 3 in the cache. Okay. So now P1, what the P1 do? P1 is initially if you see P1 in the invalid mode, so again it will go to the read only. Okay. So again, the same thing as we done in the P3. We will update the message, read request, then it will be responsible for the VAR message. The first scenario. So second scenario is, suppose P1 is in the write mode. He want to write some 0, means he want to update the value from 3 to 0. Initially in the last slide we have 3. Now let's say I want to make it as 0. So at the same time, a process running on P2 issues write x2. Now there are two writes now. You can see here. So let's say P1 issues write x0 and P2 issues write x2. So means what should we do in that case? What the Snoopy will do? So P1 will try to send the write message on the bus, obviously, as well as P2 will also try to send write bus. So only one of them should succeed. Let's say now how then they will succeed, we have to prioritize accordingly. Let's say P1 will succeed. So P1 will update cache entry to occlusive OR, because if you want to write something, you must be in the occlusive state. So we will update the cache entry to the occlusive and write 0. And now once the write is complete, so P3 should now P3 also want write at that time. So we will must push from to whatever the copy he has. You must to invalidate that copy, because the current the contents are changed to 0. So he has to update accordingly. So initially whatever the result he has to invalidate that. Then accordingly it will should update in the next slide. He have to put the read, then value response, then accordingly its value is updated. So this is about the Snoopy protocol. Huh? That's what I said. That's code on the actually it's a software part. Means we have to prioritize. We prioritize the processes. Let's say if I say P1 is a control processor, means it will deal with only control instruction and all. So that is the most prioritized. Means we have to give the highest priority to that. Huh? Yeah. Accordingly we have to instruct that the P1 should always succeed. Means if we have equal priority out of P2 and P3, then equal priority concept should not be there. Means we have to assign the priority accordingly. If you are running your control instructions, let's say on the P1, we discuss in the master slave configuration. Let's say I am following the master slave configuration. Then Snoopy protocol is that it always prioritize the master. Okay, so that's by default. Yeah. Yeah, they have to inform the master that I want to write and also. So master will control all those operations, right? So that's a notion of consistency that I already explained in the Snoopy. So same case. So then the next one, your MESI protocol. So it's you can say advanced version of that Snoopy protocol. So there are 4 stages now. Earlier we have 3 in the Snoopy, but now there are 4 stages. That's why the name is MESI protocol. M stands for modified, E is your occlusive, S is your shared, and I is your invalid. So there are four stages. Means there are 4 stages to maintain more coherence between the different processes. So invalid, the same meaning that the cache memory does not contain your valid data. Means if some write operation is already in queue, means some processor is performing write, then current processor, any other processors, they have to invalidate their own copy, because the contents are going to change. So they have to invalidate. Then we have to share. Means whatever, if I want to write something, once write is complete, so I have to share that write with all the other remaining processes, so that other processes can immediately modify their value, whatever the value in their cache, they can modify their own value and go to the new value. Okay, so occlusive, same meaning. So if I want to write something, I must be in the occlusive state. Then modified, there's one more stage added now. So modified means if the block is valid, first we have to, means if I am in the invalid mode, I can't directly go to the modified. Okay, so if it is I am in the invalid, I make it to the valid, then I can modify. So there is one condition is there over there. So we'll again discuss some scenarios. So at the system startup, means let's say all they are in the invalid mode. So we have to, if it is invalid, then obviously we have to update our data by putting the read command. So the first time a block is read into the cache of CPU 1, so it is flagged E. Now let's say CPU 1 first read it, then he wants to write it. So it will first read, then it will change its state to occlusive. That is flagged E for occlusive. So because the cache is occlusive honor, so subsequent reads. So if I write, then other CPU should be in the read modes. Okay. So what CPU do on that? CPU one in the write mode, what the CPU should do? CPU obviously it will read the same log. Okay. So the snooper in the CPU one detects the read and signal. So CPU one writes, CPU reads. So obviously CPU one, once it modify, then it will be read by the CPU, all the remaining CPU. I'm not talking about the CPU two. It any CPU in the system, they can read that. Okay, because it is connected to the buses. So all the buses are shared by all the processors, right? So CPU one holds a copy of the same. Yeah. So both entries in the cycles are made shared. So CPU one writes it. Initially, it is an invalid position. He will make it in the crucible, then write it. Then it will send the read signal. CPU now once it is read, then read is always associated with shared signal. Okay. So read state and shared state, you can say shared state will follow the read states. So once you read, so that value is shared by all the remaining processors which are in the same system. So subsequent reads in the block one, CPU1 to CPU2 will be again in the appropriate cache. Okay, so with no access to the bus mechanically according to this time. Now if CPU modifies, let's say it's already is now CPU2 wants to modify it. So CPU2 modifies a block by flagged as that is shared. So it sends over a bus to invalidate. So now the scenario is like, let's say CPU2 wants to write something. So what he will send an invalid signal. He will send invalidate signal to all the remaining PSU because he want to write something. He want to modify its contents. So he will tell all the other CPU to invalidate the whatever the copy they have because he want to write something. So that the other CPU can invalidate their copy. Okay. So he will change its states to M, that is modified. So it will write it again, then again it will be read. Means the sequence switches between those four stages, that the modified, exclusive, then shared and invalidate. Now what happens if CPU 3 wants to read the same block? So again CPU snooper in CPU detect this. It will CPU 3 will send the read request, CPU will detect it and hold the, you can say, unique valid copy. Okay. So because CPU is performing write operation at that time. So at the same time, let's say CPU 3 wants to read it. So he will send the bait signal to CPU 2. Let's means he will tell that let me complete the write, then you can read over there. So he will send the bait signal. Okay. So once memory has been updated, then CPU 3 can fetch accordingly. So this is how your MESI protocol behaves. And let's say at the same time now the control is in and the CPU 2 wants to modify. Means accordingly, means they will change all the, let's say we consider the 3 CPU. So we'll switch between these 4 different stages depending upon whatever he wants. Okay. So last option is, so finally, if let's say CPU 1 tries to write something onto the block, so CPU will detect its attempt obviously and send a signal over bus to make CPU wait, because at the time CPU is writing. So CPU 1 also want to write something on that. So initially, now as CPU writing at that time, so we'll send the wait signal. Okay. So and it's changed. Once the CPU 2 will write, so will immediately it goes to the invalidate state because now the CPU 1 wants to write something. Okay. So then CPU will change wants to write something, has to modify that. Again, it will allocate the write allocate and send the read request to all the remaining processes. So this is how your MESI protocol works. So that's what I want to say. Whenever there is a major issue, like whenever there are multiprocessors are there, or you can say the different processors are there which are running in parallel. So then coherence is the main problem. They should be consistent and they should be coherent. Means they should simultaneously n number of reads may be possible, but simultaneously n number of writes are not possible. Means if it happens, then you can say there will be nothing is means everything is unpredictable. Means you can't say whatever will be the current contents of the memory location. Okay, so that's why these protocols, there are other protocols also, but these are mainly two protocols used nowadays. Even MESI protocols used quite a lot to maintain the coherence or concurrency between the different processes. Okay, so I want to conclude now. So the conclusion is that yeah, parallel processing is a feature technique that we've seen so far for the high performance and effectiveness. Okay, so it should combine different complex hardware and software systems. Okay, So communication effectively, affinity and throughputs present. And nowadays on-chip MPs, there's the latest the things that are going in embedded systems as far as the multiprocessors. Now we are going for the multiple processor systems on a chip. So you may have heard about the Blade system proposed by the Sony, and we have cell processors now. That is again there are SIT means Sony, Toshiba, and Intel. They are combinedly proposed this cell processor, which is completely MP-SOC system. And commercial product for MP-SOC is you must I don't know whether you're done with that. You have Sony PlayStation 3 game console, if you may have heard about. So that is purely based on MP-SOC technology. This is the, you can say, future of this multiprocessor system chip. So these are the reference. Thank you. If you have any questions.